Now streaming has started.
Yeah. So Anand, can you take over?
Yeah. So welcome everyone to is it the fourth trimester now?
No, it is a colloquium, monthly colloquiums.
Monthly colloquium. Sorry. Okay. To the Bhaskaracharya Pratishthan colloquium. So today we have Jeroen Sijsling from Universiteit Ulm, and he'll tell us about Dessins and their fields of definition. Go ahead, Jeroen.
Yes, thank you very much for the introduction and of course for the invitation. It is nice to be in Pune, India, even if it's only online. So yeah, I'm going to, well, as you can see, there's two parts to this. So I'm going to talk about Dessins and then later about issues about their field of definition. But here's the talk in a nutshell, what I'm about to do. We will look at Dessins and I will tell you what those are. Those are oriented bipartite graphs on surfaces. There was a thematic semester on this also, but I will recall this theory. And these things, these Dessins, they are a way to encode algebraic geometric objects called Belyi maps. And Belyi maps on an algebraic geometric level are irrational. Well, in fact, they are morphisms. I write rational maps, but the word morphism would have been just as well. Morphisms of algebraic curves. So your x is an algebraic curve, and you get a morphism of finite degree to a P1, and you want that morphism to have a branch locus contained in 0, 1, and infinity, meaning that almost everywhere, if you look in the fiber, there's just single points, except over these points. And those morphisms are very special. And I will give you some applications of those, and I will also describe to you why there is such interest in these maps. But you can also describe them in a fairly concrete way. Namely, there is a theory of the fundamental group of the projective line -3 points, and it means that you can just understand your Dessins by means of permutations. This is one of the attractive aspects of this topic. You have three things. You have Dessins, which are a topological thing, which I will define first. And then you have permutations, which are combinatorial. And you have Belyi maps. And these all play a role. You can make these translations between these three different things. Now, as I will tell you, one of the main motivations for studying Dessins was that it was initiated by Alexander Grothendieck. It was, for him, a way to study the absolute Galois group of the rationals. This is a Galois group that you want to understand, or you are able to say, make interesting statements on. And yeah, and he hoped that new results could be obtained by studying the action of this group on Dessins. This this is still a pipe dream in the sense that it's not, this problem hasn't advanced as far as one would like, perhaps, but that is not a problem. I mean, that means that there is still much interesting mathematics to do, and it has already found many applications that I will tell you. And one remarkable fact on the way, which was in fact for Grothendieck the inspiration of the whole thing, was the following result: an algebraic curve X over the complex numbers a priori. I should have said that. An algebraic curve X over C admits a Belyi map, admits a map of this kind with a special ramification property, if and only if it is defined over Q bar, that is to say, over a number field. And that I will also tell you about. Why is that true? And yeah, I'm going to tell you about that and about a few generalizations that come with it. All right. Yeah, so what about Dessins? Dessins, well, I will first introduce these topologically, and then you can see them as a triple. That seems like a bit daunting, but it's in fact not that bad. It's basically this. You look at a graph, you call that graph gamma. It's a graph the way you know it, with vertices and edges that connect them. Moreover, you want this graph to be, I called it bipartite before, but that means that there should be a map C from V to a set with two elements, which I will call 0 and 1 for reasons that you will see later. And you want that well, this is called the coloring, and you want that the following holds. If I look at an edge E of this graph, then you can look what vertices are there at the ends of this edge. And you want every time I take an edge, the two things at the end are colored differently. So there's a 0 on one end, the 1 on the other. That is one thing you need, and you need a final thing called O for orientations, because you want that for every vertex of your graph, you want that there's an orientation of the edges. Okay, like this seems daunting when you see it first, but let me just give you an example of this. Here's an example of dessin, which you can find, in fact, on Wikipedia, but this is an image by David Epstein, who provides these and other interesting images over there. It also contains some extra information with numbers that we will for now ignore. So don't look at this, just look at the other things. You see that there is a graph here with edges and with vertices, and it's bipartite in the requested sense, because I'm just going to say that these, well, the empty ones I'm going to label with 0, and the thick ones I label them with 1. Okay, and yeah, then it's bipartite because you see it all every time I take an edge. There's different colors at the ends, and there's also an orientation. Here, the orientation was abstract, but you know, this graph is just in the plane. So let's do the following. I just take the orientation that I get by walking around counterclockwise. So here's one of my vertices over here. What orientation do I take of the corresponding edges around V? Well, I just do it like this. I orient in this way, from here to here to here. That's a cyclic way of ordering these edges, and that gives you all the information. You have a graph, you have these coloring of the vertices, and you have this orientation by the way you put it inside the plane. Okay, so that's the topological thing. Now, the thing is that you can also study this on the level of combinatorics. You can associate a so-called permutation triple to this design. It goes like this. A permutation triple, by definition, is the following. Well, you have to look at the symmetric group Sn, where n is the number of edges of your dessin, and you are going to indicate 3 elements in there, and they will satisfy this property. And conversely, by definition, this is what a permutation triple is. 3 elements over here with this product relation. My goal is sort of, how do I go back and forth between these descins and the permutation triples? I will tell you one way how to go from a given dessin, like on the previous slide, to a permutation triple. And it goes like this. You label the edges of the dessin by the numbers from 1 to n. And the sigma 0 and the sigma 1, they keep track of what happens when you rotate cyclically. The sigma 1 inverse is just the only thing that can then work to make this product 1. It's the inverse here. There's also another way to look at this, which I will not get into. Okay, so what do I get here? You know what? Let's just label my my edges. There are 4 of them here, so n is equal to 4. There are 4 edges, and here they are 1, 2, 3, and 4. Now, what was the you know what? Because so as to make my my slide consistent, I'm going to switch notation. Sorry, because I'm going to do the other correspondence from before. Otherwise, what I'm about to tell you doesn't work. I only notice this now. Sorry about that. But now the black ones go to 0. And what is the deal now? How do I get my permutation? You rotate cyclically around the vertices. Okay, that means that now I rotate cyclically like this. That gives me my permutation 1, 2, 3. And 4 just stays fixed. Because if I rotate around this one, well, I just get back to where I was. So nothing happens. That is my sigma 0. Sigma 1, that's what I get when I rotate around these two. Well, if I rotate around this one, 1 goes to 2, 2 goes to 1, and if I rotate around this one, 3 goes to 4, and 4 goes to 3. In other words, you get this one. 1, 2, 3, 4. Well, that's what you get. And sigma inverse is then sigma infinity is then determined 2. So that's how that goes. Now, you may say, yeah, but that's not a completely unique thing, right? Because maybe I label my vertices differently. Well, what the effect that it has is that you just, everything, all the permutations you have, they are conjugated by the same thing. And that turns out to be everything. What I have just done is use a bijective correspondence between Dessins of degree n up to isomorphism of Dessins, which is defined in a logical way. I'm not quite spelling that out, but just or in structure preserving maps and transitive permutation triples. So with a product equal to 1 and with a transitive action up to simultaneous conjugacy, as it's called. And the simultaneous conjugacy is that, well, you call 2 of these triples simultaneously conjugate if and only if you can find a single element Tor that conjugates all of these ones to each other simultaneously for 0, 1, and infinity, or for that matter for just 0 and 1, because then infinity also goes. That's a simultaneous conjugacy. And this is great because it makes your theory much more combinatorial. It means that you can implement things. You can just, using these permutations, you can put your Dessins in the computer in a very easy way, just by permutations. But it is even more significant because you recall that there was this sole defining relation that I wanted for permutation triples, that this product be equal to 1. Now that means that I can interpret these permutation triples that I have as a finite representation of this group pi, which is the fundamental group of P1 minus 3 points. The fundamental group is the group of loops of the homotop P, which is a group under concatenation of loops. And what you now do is, what you do is the following. The permutation, the representation of pi and you get from your permutation triple is just gamma 0 goes to 0, and it goes to sigma 0, gamma 1 to sigma 1, and gamma infinity to sigma infinity. And the reason is that you have these 3 distinguished loops in your P1, and you can see them as 0, 1, and infinity. And the loops look like this from a given base point. You go like this, you rotate counterclockwise, and you go back. And if you concatenate these 3 loops, you in fact get a trivial loop, because you can go all the way around these 3 points and contract it. So this is where this relation comes from. So a permutation triple gives you a representation of this fundamental group. Why is that great? Because you can basically use a geometric version of Galois theory. Namely, now at this point we have, given the dessin, we have this map. You send gamma I, this class of the loop is gamma in 0, the simple loops, gamma 0 around 0, gamma 1 around 1, and gamma infinity around infinity. I send these to my sigma I. Okay, that is my representation, my finite representation in Sn. Well, if I have this representation, I can ask which elements of it stabilize 1. And by 1, I just mean the element 1 of the set 1 up to n on which Sn acts. Well, that is a subgroup and it is a finite index, because there's only n things to choose. And now comes a geometric construction. That's a bit magical when you first see it, but it goes like this. If you look at look at this P1 minus 3 points, which you also denote by this symbol. And as a Riemann surface, it has a universal cover. That's a general thing. Every time you have a Riemann surface, also with finely many points removed, you can construct its universal cover, which we call U, with a projection morphism pi. And in fact, it turns out, although we won't quite need it in much detail, that this universal cover U is just the upper half plane H. So that is this H here, the complex upper half plane. Or if you like that better, you can also see it as the Poincaré disk. Now, yeah, what makes this cover universal is by definition the largest everywhere unramified cover of this P1 minus 3 points. And now comes this Galois theory bit, because it turns out that this cover, this universal cover from U to P1 star, P1 or 3 points removed, which we call pi, can be interpreted as nothing but the quotient by a group action by this fundamental group pi of before. And as soon as you know these kind of things, then you can do your Galois theory or the equivalent of that in a geometric context. And recall that we have a we have a subgroup associated to our row. Well, you know what? Let's just quotient it out, and you can then find an induced morphism, which you call phi. Yeah, this is something that interests us. In fact, you can show it doesn't depend. You could have chosen 1, 2, or all the numbers up to n there. It will give isomorphic construction. So don't worry about that. Anyway, so starting with your subgroup, which you obtained from the permutation representation, you have constructed this diagram. Yeah, they have this universal cover, which can be interpreted as a group quotient, and you made this intermediate thing over here. Now, this thing here, U, that's universal cover, that's not an algebraic curve. But there is more to be said on this side. In fact, this map here, phi, is finite, basically because it's constructed by means of a subgroup of finite index. And as long as you have finite covers of Riemann surfaces like P1 star, what you have upstairs, this quotient of U by H, that is in fact again algebraic. So in fact, this thing is too large to be completely algebraic. You cannot find, this is just the upper half plane. You can't make that into an algebraic curve, but this one you can. That's sort of the idea. Oh, and by the way, maybe I should have said this. Every time I write this skew line, it just means quotient by a group action. I just write the quotients on the left, that's all. So here I divide out by the full action of pi, and here I divide out by the action of this subgroup. Anyway, now I've told you this is an algebraic curve. It's just a P1 minus 3 points. And because this is finite, we also obtain an algebraic curve here. Now, this algebraic curve is not proper, by which I mean there are points missing. You can still compactify it and you will get additional points. But that is fine. We have constructed our phi here, and it goes to P1 star, which also itself misses 3 points. But it turns out that you can complete such a morphism by the usual dictionary between field extensions and or function fields and morphisms of smooth projective curves. So we do that. We prolong phi, and you say you just sort of, the usual term, I don't know, people often call this to fill up the holes that are remaining in these algebraic curves. I make my P1 minus 3 points into a P1. I get an X here, and this becomes a map phi, which by definition can only be ramified in 0, 1, infinity, because after all, your phi was ramified everywhere, just like this pi was. If phi had ramification, and so would pi have, but I constructed this otherwise. So now there is this theory of fundamental groups, and it tells you that this, in fact, gives you another equivalence between transitive permutation triples that we saw before, up to the simultaneous conjugacy, and now something completely algebraic, unramified finite morphisms, maps between curves, whose branch locus is contained in 0, 1, infinity. And this time, the equivalent of conjugacy here is this isomorphism of covers. What is that? This. Two pairs. It's a pair because you have both X and your phi, so sometimes I denote it like this. Yes, is a question.
Do you mean ramified finite morphisms?
Yeah, I don't know there should not be no unramified here. That's nonsense. I don't know how okay. Completely ignore that word, please. Finite morphisms.
Finite morphisms.
Yeah,
Okay, yeah.
I could have said it differently. Thank you very much. You can say this differently. It's right this way, the way it's written now. Finite morphisms whose branch locus is contained in 0, 1, infinity.
Great. Yeah.
Meaning that it's unramified everywhere else, above the other at the other points. Yeah. And yeah, and I have to tell you, when are those two things isomorphic? Well, following condition. Suppose you have two of them, x and phi and x prime and phi prime. You just want it to be a map upstairs that makes everything commute. Okay. Yeah. Now, this is a bit, it may seem very strange because, yeah, you may say, sure, okay, maybe there's a weird theory of the fundamental group that allows me to do this, but you have just done something strange with permutations. How is this? How does this give me something convincing? But in fact, you can understand this quite intuitively because, for example, if you have a pair x, phi, so map from x to P1, then you have a dessin in the following way. You look at the interval 0 and 1 on P1 and you take its inverse image. And that will give you a graph. And since the points 0 and 1, they may ramify, you get these possible multiple edges that meet at those points. That's how it works. You just mark the vertices of this inverse image by the points above which they are, 0 and 1. Just mark them by the number to which they project. So that is one thing, and that makes it already quite a bit more intuitive. There's also another thing that you can do. Next logical question is, suppose that you come to me with a permutation signal, sigma. How then can I find this x, phi? Well, here's a sort of vague and hand-wavy answer, but in fact, it has to be vague because it's just something difficult. But you can think of it like this. You have your three permutations, sigma 0, sigma 1, and sigma infinity. And now you can obtain a topological cover, and I should perhaps say a topological cover of P1. So of the projective line over C, so in fact of the Riemann sphere, by taking n sheets and you sew them together above 0, 1, and infinity by the way that these permutations tell you. So before you had the permutation 1 through 3, that means there you sew them together with the right orientation. And this is a cover, and it's a topological cover, and it comes with a map to P1. And a priori, this map is something purely topological at first. But now there's the thing, if you have a map from a topological surface to a Riemann surface, you can always pull the complex structure back. And that gives you a unique structure on this thing upstairs, which now you call X, that makes it into a Riemann surface. Phi becomes a map of Riemann surfaces, and then you use the other dictionary, which tells you in algebraic geometry that maps between Riemann surfaces are just maps between algebraic curves. If everything is complete, which it is in this case. You have only looked at completions here. Now remember, we completed everything. So you get this dictionary, and that works. But that's just sweeps things under the rug because you do quite transcendental things. I say you lift the complex structure well, but how does that really go? You know, that's theoretically true, but to actually do this is another matter. But that is how you can think of it. But also good now is just to look at some examples. Because, yeah, you can see that it's still the same mistake, but now I caught it before. If you now look at these finite morphisms, whose branch locus is contained in 0, 1, and infinity, well, those are also just called Belyi maps. Those are the maps that I told you about in the first slide. And here's the first example of it. You can take x is P1, just give it a coordinate x, say, and here's your phi. Phi just is this map. And now you see that if you, what are the originals of 0? Well, you see that when it's 0, you get a triple root at 1 and the single root at 9. And you can also ask what happens with 1. Well, for that, you look at phi minus 1, and there you see, hey, there's a square here. So you get a double root at whatever the roots of this polynomial are. In fact, those are quadratic points that I won't write down, but which will appear in a which will appear later. Anyway, yeah, like I said, you have 2 points over 0, ramification index 3 and 1, because of the exponents. Well, you can write a 1 here if you like. Here you have 2 of index 2 because there are 2 points corresponding to this factor, and there are 2 points over infinity. Which one, in fact? Well, you see x is over infinity, that goes to there, but also infinity itself. Infinity itself is, in fact, ramified of order thrice over infinity. Well, and this is exactly the descent that I showed you before. And also the points are marked. These are the 2 points that correspond to the roots of this polynomial that I showed you here. See, if you determine what those roots are by means of the ABC formula, you get these 2. So yeah, that works. So these are the points over 1. You also see the points over 0, and you see that you have the right ramification indices. 3 for 1, 1 for 9. And if you, in fact, take this inverse image, this one shows up. So you can really just say this is a map that corresponds to these permutations. I think it was 1, 4, 3. Yeah, this is how it goes. It's a bit funky. I mean, you write down your permutation, all of a sudden it has to do with such a map, but that is just how this is. Here are other examples, just to show you some in a different context. This is from a database by Beukers and Montanus, which I will tell you about later. These maps are written in a bit more schematic way, but basically what you should think of here is you see these points of order 3 coming together here, and those are all above 0. And on the middle, on the midpoints of all these edges, there are points above 1, and then the actual edges are the ones that you see here. Well, why did I show you this? Because this gives you a nice example of complex conjugation on Dessins. Because now look, here my dessin was quite pleasant. We had these nice coefficients, but they're just in Q. That doesn't always happen. Sometimes your coefficients are just over a larger field. And then you could have, in principle, something like 9 plus I here. Who knows? Well, don't do that because it won't give you a dessin. But let's just to fix our thoughts, the coefficients here might be in the over number field. But then you can apply a Galois conjugation of a given Galois element, and it will change your dessin. And what you see here is that you see 2 descins that are mirrorings of each other, reflections, and those are in fact obtained by means of complex conjugation over a cubic field. But in fact, this whole thing is a single Galois orbit by means of conjugating the defining equations. These drawings transfer to one another, and that's what makes this whole thing really, really strange. Oh, sorry. Yeah. Let me do another example. Here's yet another example that shows what strange effect Galois conjugating defining coefficients can have. We can take axis P1 again, and you can take this Belyi map. It is a rather large factor that comes in front, but that just happens. And you see now, these are not defined over Q. You need the square root of 21. This one is defined over R. So complex conjugation won't do anything to it. They will be nice and symmetric. However, they still change when you go and you take a Galois element that maps square root of 21 to minus square root of 21, and this happens. You get these 2 descins. One of them corresponds to one of the choice of the root, a minus here and a plus here. And the other one corresponds to the other choice of root, a plus here and a minus here. And these are transferred to each other by conjugation. I hope it is at least slightly convincing, because you can see that the ramification is right. There's a to the power 3 and there is 2 to the power 2. Well, you see that here too. 1 to the power 3, 2 to the power 2, and also in this one. But these descins are not isomorphic, but they are Galois conjugates. This is a non-trivial example of Galois conjugation, and this is something, in fact, that turns out to be really, really useful in the context of Galois theory, because there is this theorem, which I will tell you a bit about some of the details of this. It's a theorem by Belyi. And it says, if you have a smooth projective curve over C, over the complex numbers a priori, then the statement is, X admits a Belyi map. That is to say, given X, I have X in my hands. My question is, can I find for X a map P1, a 2P1, which I call phi, that is ramified only above 0, 1, infinity? That's a reasonable question to ask. And the very surprising answer to this question is, you can do that if and only if it's defined over a number field. And this is strange, because it says you have a certain geometric property if and only if you are defined over something arithmetic. And that is what makes this fascinating, this link between geometry and the arithmetic. I won't do this proof. We are going to talk about one direction later, but the crucial direction, the direction that wasn't known at the time that Belyi proved it, was the following. Belyi proved this direction. If X is defined over a number field, then it admits a Belyi map. That is what he did. And I won't, like I said, I won't tell you about the proof, but it's an extremely clever proof. But it goes like this. You just take any map from X to P1, some non-constant function. Well, that always exists. You have an algebraic curve, and you post-compose on the P1 to get your branch locus all the way inside P1Q. And then you post-compose yet further. You use maps. You apply after this map, you apply maps that make a certain branch locus smaller, and you keep repeating that and repeating that until your branch locus is just all the way inside here. Like I said, this is tricky, extremely clever, but this is the idea. It's a completely explicit, finicky proof, but it has a very important corollary, namely that if you look at the Galois action of the absolute Galois of Q bar over Q on the set of isomorphism classes of Belyi maps, then that is faithful. Meaning, well, you'll see what it means in the proof, but it means that every time I have a non-trivial element of this Galois group, it acts non-trivially on some dessin. And here's how that goes. If you know Belyi's theorem, this is in fact kind of easy, as long as you know that you also have elliptic curves, because you do the following. Suppose you have an element sigma, and it's non-trivial element of the Galois group. Okay, non-trivial means that some algebraic element is moved by this Q bar, by the sigma. Okay, so I choose one. I call it J. Just take any J over some number field. I don't know what, but just some in the algebraic closure. Then you take it such that it is moved by sigma. Good. Take an elliptic curve at J invariant J. You can do that. There's formulas that give this. And now Belyi tells you, okay, given your E, which is defined over a number field, because I just took an elliptic curve over Q bar with J invariant J, Belyi says, I can find the corresponding phi. And my claim is this is mapped to something non-isomorphic by sigma. And that is clear because you can never have an isomorphism here, because remember, for the isomorphism, I needed a diagram like this. I would need this to the P1, but I would at the very least need a map here, an isomorphism here, and that doesn't exist because the J invariant tells you that these things are not isomorphic. Sigma E has J invariant sigma J. And that's not equal to the J invariant of J, so it's completely excluded as it exists. And that means you're done. So your action on Belyi maps is faithful, and therefore also the action on Dessins and on permutation triples. And all of a sudden, you have this topological way of studying the Galois group. All the information of the Galois group by this faithfulness is contained in its action on Dessins. And now I'm going to do something terrible. Namely, I'm going to show you a slide which is completely full of words, which you shouldn't normally do. Yes, is there a question?
I just have one question. When you complete E, the field of rationality remains the same?
Yeah, that is in fact an important, good point that you mentioned, because in general, that is an issue, and it is in fact the very issue about which I will talk later. But for elliptic curves, there is a trick, and it goes like this. You look at this elliptic curve. And you look at its J invariant, and I don't quite remember what it is, but if you call this EA, then G of EA is a fractional linear transformation in A, meaning that you can invert it too. And now suppose that someone comes to you with your favorite J. Then you just take the inverse fractional transformation, put that for A, and that will work. And that is then defined over Q bar, because your A as a fractional linear transformation over Q of this J is in fact also in Q bar. Okay? But you're right, this is a very important point also for curves to be able to do this. But in fact, there is never a problem for curves. There is never a problem of descent from C to Q bar. That is always fine. Okay, so you can find this on the curve, and with that you can do it. Yeah, and now I'm about to show you some quote by Grothendieck on this theme. And I'm telling you this because this is in Grothendieck's sketch of a program, as it's called. It's written in French, but obviously this is translated. And he was very astonished by this result. He says this, he uses a bit different language, and he says every finite-oriented map, so every dessin, gives rise to a projective non-singular algebraic curve defined over Q bar. And I want to know, do I get everything in this way? Who knows? And well, then he says something more erudite. Can I then interpret every algebraic curve over a number field as something, as some modular curve? Well, I really didn't know, and I was almost embarrassed to submit it to the competent people in the domain. And Belyi, well, he didn't have any counterexample at his sleeve. It seemed crazy to him. But then Belyi proved this theorem, and this astounded Grothendieck. And never, without a doubt, was such a deep and disconcerting result proved in so few lines. In fact, there is a terrible pun in the French version of this letter, because he writes, "It is the proof fits in two little pages of a letter of the linear." And in French, this fits in 2 little pages of a letter of 2 lines, because the linear means 2 lines in French. So this is French humor. Never mind. Grothendieck's dream was that you can study the action of the Galois group by this action on Dessins. Now, that is not, like I said, finding very meaningful invariants in this way. That is yet a project that is to be completed, but it has found many Dessins and found many other applications. One of them exactly what Grothendieck said. If I have a curve over Q bar, then I can give it a modular interpretation because it corresponds to a certain Belyi map. And via Belyi maps, I can in fact give it a modular interpretation. And Will Chen has made this explicit. Other things is that you can compute equations of certain Shimura curves by this, just by reducing it to computing certain Belyi maps. You can do the same for elliptic K3 surfaces, which was the list of Beukers and Montanus that I showed you before. You can realize the monster group as a Galois group by rational rigidity and specialization. This is how it was done. Basically, people constructed a suitable Belyi map and then specialized in the fiber to obtain an extension that had the monster group as a Galois group, which is a really nice achievement. And you also get good ABC triples when you specialize in the same way. In fact, Elkies used Dessins and Belyi maps to show that the ABC conjecture implies a Mordell conjecture. So this is very worthwhile. I mean, even though the theme didn't quite work out yet as intended. Now I want to tell you about some other subtleties, and those are related to the other direction of Belyi's theorem, because I told you one direction. Belyi showed if I have a curve over a number field, then I can find a Belyi map Well, this is the other way. Suppose you have a Belyi map, x comma phi, so map phi from x to P1, then this x is automatically defined over a number field. I'll tell you what defined over means later in precise terms. But here's the intuitive idea. If you just walk up to an algebraic geometry in the street, so to say, this is what they would say. Well, if you look at the degree of your phi, so the degree of the Belyi map, the number of edges, well, then a set of isomorphism classes of Dessins with that number of edges is finite. For example, because it's just, you know, something with permutations, it's a finite set. So the set of Belyi maps with that property is also finite. So you just look at its moduli space, and it's of dimension 0, and all its points show up over Q bar, and that's the fact that they all show up over Q bar means that you can find equations for the Belyi maps and for X itself. That is what, like I said, what the intuitive argument for it is. But this is not a. There are, of course, gaps in this argumentation. Is there a moduli space of Belyi maps? Yeah, how do you make it precise at all? Why is it so that when the points show up over Q bar, that you have equations over Q bar? So it's very plausible, but actually to write it down, that is something else. It's one of these well-known things, but when people say well-known, it just means someone else knows this usually, right? So I don't know. There's some amount of effort involved. And to make this heuristic argument precise, I need a definition, and that is the field of moduli. Okay, so we're going to look at the Belyi map. So this pair x comma phi. And I'm about to define the field of moduli, and it's this. You look at all the automorphisms of C, I call them sigma, with the property that if I apply sigma to the defining coefficients of both x and phi, so if I look at my conjugated Belyi map, then it should be isomorphic to the original in the sense described before, that you can make this triangle that makes everything commutable. You look at that group, and you look at its fixed field. That is the field of moduli. So the fixed field of this subgroup. And the point is that if you have a Belyi map, then it is a number field, first of all. And that is because it's basically because you can show it's a finite index and in odd C, and also some technical property that then shows that it indeed corresponds to a, well, it's a finite index. It will correspond to a number field. Why a finite index, by the way, is simply because there is only a finite number of Belyi maps up to isomorphism of a given degree. So you cannot move too much when you start conjugating here. Okay, you get a number field. And this number field, mx comma phi, is the smallest field of which you can hope that there exists a pair x0, phi 0, and those are over this field. So this mx phi is that is where these both have admit defining equations, and I want that pair is just my original pair over C. That is the smallest field for which you can hope that it exists, but it doesn't always. And it is somewhat surprising because in the classical Gauss theoretic context, this is not a problem. Huh? If you have an element and it's invariant under a certain Gauss group, then it should just be in the corresponding field. And now I ask the same questions for isomorphisms, and all of a sudden it's not true. That has to do with certain cohomological things that I will show you later. But for now, let it just be mentioned. No, in general, you cannot do it, which is annoying, right? Because then, but then what do I know? Can I then still, if I cannot find a corresponding model over this field, which field else then? Do I need an infinite extension? So you start doubting and you start asking. But here's a nice classical construction by Koch, who was the first to make this explicit. All these heuristic arguments here. And this is what he did. We take a non-ramification point of phi. So P is on X, in fact, should have said that. P is on X, and I take it that it's a non-ramification point, so no, maybe just not above 0, 1, infinity, and you take it with rational image. And rational just like a fraction. Now you look at the field of moduli of a triple. not of x comma phi, but as a triple. And you do the same thing as before, but you also want that your isomorphism sends this point to its conjugate, or rather the inverse. Okay, you get a fixed field. Of course, you have added the condition. Yeah, so it may be larger than your previous field, but that doesn't matter. This field is still finite because, again, you have only the fiber is finite. So this can only go wrong for something of, this goes right for something of finite index. And then there's a theorem by Cook, and it says, if you look at this pair x comma phi, yes.
I assume in the earlier slide we're not really looking for some x naught comma sigma naught. We just wanted the conjugate of x, right? So why do we look for x naught phi naught? We are interested in the conjugates of x. Like in the definition, when you look at the earlier slide, we are only looking at sigmas, that x sigma. I mean sigma of x comma phi of sigma. So why do we look for a pair x naught phi naught generally, which is not may not be related to x, right? I mean,
let me be sure to understand your question. Is your question, we were looking at x being defined over number field, why do we look at this triple?
No, sorry. Can you go to the previous slide?
Yeah.
Yes. So here you are asking that maybe it is the smallest field over which we can hope for existence of pair x naught comma phi naught, such that we have an isomorphism. But this x naught, we are interested only for sigma of x, which is like kind of the conjugate of x, right?
I don't know quite what you mean, but x naught and okay, maybe x naught phi naught, they're over m x phi. And that means that if you take these things and you conjugate the defining coefficients, they won't budge. They will just stay the same because they're over the field that is fixed.
Sorry, what is sigma of x in the definition of H?
That is the x with defining coefficients conjugated by sigma. Yeah, and suppose that this idea is true. Suppose you do get an x0 phi 0 over mx phi. Well, mx phi was well, I mean, how should I say this? If I take an, I have looked at the, I'm looking here at the fixed field of this. Yeah, so you know what? My claim is, suppose I have x0 phi 0 over mx phi. Then my claim is, if I now conjugate, if I now take sigma x0 and sigma phi 0, they will just be the same, just really the same, not even isomorphic, just the same. And it is because if you look at an element of sigma of the relative Galois groups of C over mx phi, then that fixes the elements of mx phi, but x0 has defining equations in there, so it won't get moved.
Okay, yeah. Thank you. I get the point.
Okay,
thank you.
Thanks for the question. Yeah, but that's important. And Cook does something else. He makes his field a little bit larger. He says, okay, you know what? Make this subgroup a little bit smaller, making the field larger. So yeah, now we look at the fixed field of yet a smaller group, but it's still a number field because of the finite fiber. Yes, is there a question?
Yes. So in the previous slide, the fact that the field of moduli may not be the field over which you have the x and phi.
Yeah.
Is that an issue if x phi has no automorphisms?
Yeah.
Still an issue?
That's right. If in fact this pair x comma phi, if it has no automorphisms, then there is no problem at all.
Oh, okay, great. Okay.
Or you know, if it has no non-trivial automorphism, I say this all the time, but you know what I mean.
Yeah.
There's always
thank you.
Okay. Yeah, that's it. And that will show up too later. Yeah, and Cook says if you make this field a bit bigger, then you can always do it. And then you're happy, right? Because this is still a finite extension of Q. By the way, is there still a question, or is the hand still raised from before? Okay, great. Yeah, so here's how this goes. I should sketch how this proceeds. It's a very elegant proof. you do this. You take your point, and remember this point was a point on X. It doesn't ramify, and its image is over Q downstairs. Good. Now, Cook says you take M minimal with the property that if you look at the global sections of this MP, it's 2. Well, then you can find a Z such that this holds, and it's dimension 2, and of course the constants are in there. You take your Z, and then he shows that in fact this generates a function field of X. The function field of X is generated by this map phi to P1 that you already have, and your new Z. That's step 1. Step 2 is there is still some freedom in your Z, because you just have to take, you could still take a fractional linear transformation of it, or an affine transformation, I should have said, and it will still satisfy this property. And he says, well, okay, then just make sure that you do the following. You look at this phi minus q. Phi minus q is a function on P1 that in fact uniformizes locally at Q. But because P ramifies simply, it's also a local uniformizer at P upstairs. Okay, develop it. Modify Z in the following way. I know that Z has full order M exactly, but he says scale so that there is no constant factor in front. Just make it the factor 1, and then you can also scale such that the subsequent term here that is also okay. Okay, now comes the argument. He says, maybe you should constant. I think I'm talking nonsense here. There should be a constant term 0, not this. It will have this in general, but it should have constant term 0. So it's just that now that I tell it that I realize that it's off. Anyway, but now comes the argument. He shows that in fact this function Z is invariant under this group, under this aforementioned group. And since this function is invariant, so is its minimal polynomial over C phi, which by the way exists, because this extension is a finite extension of C phi. This is exactly the dictionary between function fields and algebraic maps. You know that there is this, that this gives you a finite extension of degree n. And he says, well, this function is just invariant under this, because if you conjugate by such an element, well, then your phi, your x and phi are respected because of the condition here. Your x and phi are mapped to isomorphic things. See, that's what it says. You can pull x and phi straight after conjugation by sigma, but under conjugation by the sigma, remember also this sigma p is mapped to p. And if you then take this corresponding isomorphism, which exists by construction, then your Z moves along under this isomorphism. But you know that before it had this nice Taylor development, and because you normalize this Taylor development, this is also just remains true for its conjugate. That means it's invariant, and then so is the minimal polynomial, and you have a re-equation over this field. It's simply the minimal polynomial of this function over C phi. There's an alternative version which I'm now looking at with Harsha and with Devendra, which is sort of similar, but a bit more canonical. You take P as before, and you consider a sheaf, which I call L. It's just a sheaf obtained by taking multiples at P. You may also want to take a plural canonical sheaf. Now you do the following: take a basis of global sections of this sheaf, this space V is a V of global sections, and you rewrite its elements as power series in terms again of the rational uniformizer, which you can use because this is a locally free sheaf. Get an isomorphism here by construction, which depends on the scalar, but later it won't matter. And this follows from the fact that it's simply ramified. Well, and now you just actionalize. You can now take all these Taylor expansions in the rational uniformizer, and if you actionalize accordingly, this corresponding embedding with respect to that particular echelonized basis will give you a model over this field. The subtlety is always over which basis you have to take it, but it should be this basis that we found here. Okay, a few more things that I want to tell you at the end, because yeah, there were two things I mentioned already. There was a cohomological obstruction, and there was also a relation with automorphisms. I'm going to tell you about that now, because this is great. We have found a model over this field, and that's a number field. So that means that we have proved Belyi's theorem, or at least one direction of it, which is wonderful. The question is, can we descend all the way to mx phi? Well, you can't. Well, you know that because I told you so. So that doesn't really. That's just bluffing, but there are really criteria that allow you to check this. And this is a really nice criterion by Vey, and it says the following: when can a descent is paired to its field of moduli? Well, remember, I wondered that there would always exist isomorphisms from this to this for all sigma. And Vey says, in fact, that works as long as a certain compatibility condition is verified. This one, that's a co-cycle condition. Both of these, they are isomorphisms, in fact, between sigma tau of x and x, but you want them to be equal. And that is a real condition. You have to fix your I sigma in such a way that this holds for any pair sigma tau. Yeah, and here's the corollary then. No automorphisms implies descent, as you said. This is true because, yeah, but like I said, both sides here, they are maps from sigma tau of x to x. So if there are no automorphisms, well, then they're the same. If two isomorphisms here, and any difference between two isomorphisms is an automorphism of x, and it's only the identity, so they would coincide, and you will get the descent. There's another corollary of this, namely, suppose I take the automorphism group of this pair, and you can quotient it out on the left again. And because of the fact that you are making all your automorphisms trivial in this quotient, this will descend to a model over the base field. Oh, I shouldn't have called this. Ugh, this is really stupid. Okay, this is I should have called this B. I should have written B0 here. Okay, so X will in general not have a model over this field, but this quotient, which I call B, does. And then you can look a little bit differently at this result by Cook, because his result comes down to saying, well, not quite, but you can interpret it as saying that if B0 admits a rational point over this field, and it is descends, because as soon as you have a rational point on this thing, then the point in the corresponding fiber will give you a will satisfy that mx phi is mx phi p, and then you can use Cox's theorem. Just want to close with one funny thing, because there's the case descent from C to R. Yeah, how do I go from the complex field to the real field? And I already told you a little bit about what happens there. This was done in detail by Couvenier and Grandboulin, and it says the following: suppose you have a descent B, what then does the conjugate Belyi map correspond to? The complex conjugation of the Belyi map. So complex conjugation of the defining equation of x and of the coefficients of phi. Well, as you will probably believe intuitively, that is just a reflection of your descent. Complex conjugation corresponds to a binary reflection of your descent. And the result is D has field of moduli contained in R if and only if it's isomorphic to D bar. Well, that's not the result, that's just definition. But here is the result. There's a field of definition contained in R if and only if the aforementioned isomorphism can be chosen to be of order 2 on the level of permutations. And sometimes it's of order 4 and you don't get it. And here's an example of that. This is the sample to be 16. Yeah, because you can count the edges, there's 16 of them, it's just 4 times these 4. Now my claim is this thing has field of moduli contained in R but does not descend to R. Because in fact, what happens if you reflect this descent, You can see what happens if you just reflect it over the horizontal axis, for example. What you will get is you get the same dessin, but it's turned by a quarter. Well, I think counterclockwise. Anyway, it's if you reflect it, it's isomorphic to itself, but by a quarter turn. And that means that to get it back, you need to apply an isomorphism, which is of order 4, and it doesn't work. And this is in fact, okay, I had written some more examples in the other slides, but this is in fact the smallest dessin that has a field of moduli, which is not a field of definition, not just for R, but in general. This is the smallest dessin for which you get a problem at all. Yeah, so I've just presented this as being a something that we need to understand, and this is true, but almost always, in small degree, the field of moduli is in fact a field of definition. I should tell you quickly why this is. Why is degree 16 the first degree in which this occurs? Well, in all other degrees, one of the following things happens. Either one of the fibers of phi over 0, 1, infinity has a point with a uniquely occurring ramification index, and as soon as that occurs, then you can use this point in Cox methods, and it will show you, well, the fields of moduli are equal because it's the unique point with the ramification index, so it has to be mapped to its conjugate when I conjugate because of the uniqueness. Well, but then you have this equality, and Cox theorem gives you the result. Or the canonical model, here it is B0 again, has another sporadic point over this field of moduli. And in small degree, this always happens. I had another example here where you can really see this in action, but I think I will leave it at that. So the message is, this is really a problem for the sense, and it will happen that this gives you that these ascent issues arise. However, it is a phenomenon that is whose first occurrence is in degree 16. So that is a bit of a relief, perhaps. On the other hand, it will be very interesting to study issues of descent and the like, in also for the sense in detail. It will be a very nice source of examples. And I will stop there. Thank you very much.
Yes. Yeah, actually, is it computationally possible to decide whether this Belyi map exists in the case when we have this nice branched covering? Is there some way of deciding computationally existence of Belyi map, at least in some cases, some simple cases maybe?
Yeah, I don't know, in fact. And this is a thing that I'm also doing some research on. Very often you can decide it, because very often this canonical model, you can show it has a point and then you're done. So it's usually, okay, let me put it like this. It's usually quick to decide, but if it descends, then usually you will find it quickly. But there are issues, because I told you, if this thing has a point, the B0, then it descends. But that is not an equivalence. It is just one possible criterion. And in general, I don't know, to be honest.
Maybe
and in fact,
attempts about it.
Sorry?
I mean, there may be some attempts for people try to write, algorithms.
Yeah, definitely.
Various problems. So maybe in some cases it is successful and good algorithm one gets. Not always.
Yeah. There are many tricks that work also, ad hoc tricks that you can use. Sometimes you can find, okay, sometimes maybe the canonical model doesn't have a point, but you can find a way co-cycle by hand. You can get lucky like that, but I do not know of a general method to say it descends or not. And in fact, this is for the following reason. There are also conceptual reasons for this. First of all, descent is not a local to global problem. It's not true that if it descends over all completions, then it descends over the field itself. So it is an arithmetically challenging problem in that sense. Moreover, there is a theorem, I think that this is a general theorem that was done by Belyi and some of his co-authors, that shows that in fact the existence of a descent comes down to a certain higher dimensional variety having a rational point. And of course, those are not easy problems in general. So yeah, we shouldn't expect it to be easy, but we may get lucky or get a good grip on these things in some special cases. Yeah. But this is in fact why it's so interesting also, because it will also give a very good source, I think, of counterexamples to descent. Exactly. So it's exactly the fact you cannot get to it that also makes it fascinating. Yeah.
Yeah, thank you.
Yeah,
Can I ask it? Oh, sorry.
Yes, sir.
There was a question. Sorry.
I have two questions. So in these examples, can we compute some x naught phi naught which is defined over the field of moduli?
In which examples?
So yeah, you said this is the smallest counterexample where the x comma phi is not defined over the field of moduli.
Yeah, this is one.
Right. So, but by definition of the field of moduli, there should be some x comma phi which is defined over this, and I mean some x naught phi naught. So, do we know that x naught and phi naught in this context?
Yeah, I think in this specific case we do know it, yes, but I don't know. I don't know if you want to see it, because I'm saying this because there's a whole whole other issue of the calculation of Belyi maps. Sometimes the coefficient, there is research on this, but the coefficients get a bit large on. I think. Okay. Well, I had this other counterexample where it does descend, so it's a non-counterexample. That's how I called it, what I called it. And there you can really determine the descent in the end, although it's not written in the slides. So if you, in fact, manage to find a Belyi co-cycle, then you can also write it down. If you do not, for this one, however, I do seem to recall that I think you can, yeah, this should be okay, because it's a degree 2 cover of another dessin, and I think you just have to, I think, okay, don't quite believe this yet, but what I think happens is this. This thing has an automorphism group of order 2, as far as I remember. Yeah, I mean, that makes sense, because otherwise, yeah, it should be order 2 here. It certainly is not trivial. Okay, that means I can divide out this automorphism group to find another dessin. That's of degree 8. Yeah, I can pull my dessin apart. I have my x, my phi to do this degree 2 quotient first, and then my degree 8 dessin. That degree 8 dessin for sure is written down somewhere. I don't know where, but it's somewhere. And what I think will happen is that this degree 8 dessin is on a curve of higher genus, maybe on an elliptic curve, and then no, wait, this is a genus 0 descent. That's not true. No, it's even better. You have a okay, the dessin of degree 8 that corresponds to this is likely to live then on a conic, and then the descent in this case probably comes down to taking a degree 2 cover of this conic, and that is not always possible over the base field. It's that kind of issues that play a role here. Yeah, I think that's it. Because yeah, you can always take a degree 2 cover of a P1 over a given ramification locus. You just write down a polynomial, you put y squared in front, but it doesn't work like this for conics, because there's always the issue you have to subtract a suitable anti-canonical divisor. I think that's what happens here.
So
yeah.
that conic may not have a rational point.
Yeah, that's it. I think, but I'm starting to doubt what I say now, because
I had a topological question, I mean, not very arithmetic. How do you read off the genus from the graph?
That's what the graph is drawn on.
Oh, I see.
And in this case, it's drawn on the plane.
Yeah.
It's genus 0.
So it's the I get, okay. So
It's a number of holes in the topological surface on which it's drawn. So yeah, this sense they may not look like this at all. You may just take a donut and start scribbling on the donut, and that works too. Yeah, or on a pretzel or whatever.
mhm.
And I have one more question. I mean, not really a question, more of a reference. So, like, you have given examples of Belyi maps from P1 to P1. Like, if I want to construct it from some general X, so is there a place where we can find a few more examples to look at?
Sorry, what kind of examples?
Examples of Belyi maps on general X.
Yeah, I didn't include it. Yeah, they for sure. Okay. If you want, well, it depends on how I want to look at it. But there's two answers to the question. The first is if you want to have Dessins that are on Belyi maps on surfaces of higher genus, you do this. In fact, it's good that I can make this advertisement because it didn't quite fit in the talk, but it is very useful. You go to this website, beta.lmftb.org. That's the LMFTB, but it's the beta version. Yeah, so not everything in there, it has to be polished. But there you find a tab and it's called Belyi maps. And this contains results of Michael Musty and Sam Schiavone and John Voigt, who have been working very hard to make these databases. And there you can just search for I want genus 2. And you will get examples. If you want pictures, you can go to my website because I have a master's thesis on there. This is there's a lot of mathematical mistakes, but in my master's thesis there's some drawings of this sense on donuts. Yeah, there's a section called notes, and you will find a master thesis there.
Okay, yeah, thank you very much.
Yeah.
Thank you.
Thanks a lot. It was nice talk, and it was the last one in this series.
Nice to be here.
Thanks, and share the slides also. Yeah.
Thanks,
Yeah, I will.
Jeroen.
Thank you.
Thanks, Anand,
And
for
thanks everyone for attending.
Thanks very much. Have a nice day, everyone.
Okay, thank you.
Thank you.
Bye-bye.
Bye.
stop the recording and the things,
Okay.
and
Good.
live stream also.
Yes.
See you, Jeroen, sometime.
See you next.